Let's, with the remaining time, go through semi-gray surfaces and how you solve these. It's not too different from what we've done already, but it's just a little bit more bookkeeping, which is maybe the story of this class. A little bit more bookkeeping. Okay, what are semi-gray surfaces, first of all? So remember back to this idea that if you have, let's say, an emissivity as a function of wavelength like this, and it looks like that, you could model that surface by breaking it up into discrete sections and then handling each section separately. So we said, okay, we could model this as a constant, we could model this as a constant, and so on. So if I'm going to do that, I'm going to need to modify my set of equations that we've already developed to make sure that we account for the fact that radiation emissivity can be different in each of these specified bands that we have. So the general approach for this is you say, I'm going to take some low wavelength, some high wavelength. Let's call this lambda low, lambda high, in section 1, and specify an emissivity, emissivity 1. In section 2, I would specify it 2, and so on. Or we're going to use the index W, so lambda low W to lambda high W. And then we're going to go all the way up to NB, or N bands. That's an integer value of this index W, and then formulate equations for that. All right, so how do we modify the approach for this? So let's maybe get some definitions down here. So I'm going to say that Q dot I, right, this is heat transfer from surface I. Now in band W, Q dot IW, that is the heat transfer associated with surface I in wavelength band W, is equal to, or is, just defined as the net radiation for surface I band W. And that would be written as Q dot I is equal to, it's written the same way. We have the same energy balance. It is related to the total heat transfer, Q dot I, by just summing all of these up. So it would be summation of W equals 1 to NB of Q dot I W for each I equals 1 to N, where N is the number of surfaces. Right, this is our total radiation for surface I. So a little confusing. This is the band specific, this is a summation. So this is just saying we can discretize the surface and take each bit. Okay, there's also the need for the black body emissive power. We're going to take EB for surface I, discretize that into index W. So this would be the black body emissive power for surface, surface I in band W. And what this is actually equal to the integral from lambda low W to lambda high W of the black body emissive curve. So EB lambda I, d lambda. Right? So this is at some Ti. So what that's saying is we have to evaluate the black body curve, that's Planck's equation, from one wavelength to the other. And then that becomes this value which would sum together to give you the total black body emissive power. So how do we remember how we do this? We have that external fractional function that we use. So we called that, I guess I called it F. That is our, we'll call it EFF, external fractional function, F. We evaluate it some Ti from lambda low W to lambda high W times sigma Ti to the fourth. All right, that's how you're going to evaluate the amount of black body power that's in that segment. So we need that. And then what else do we need? I guess we just also need to I'm going to add it down here at the bottom so I have room, but we also need J, I, W, right? And that's just the radiosity. Radiosity, I, comma, W, right? So it's the same indexing. So we need all this stuff, just as we do for the other models, but I'm just making clear what the indexing is on this. It's a little tedious. The important points are that heat transfer sums up, black body emissive power sums up, and we get this by evaluating the external fractional function. Okay, so if we know that, then we can rewrite our equations up here. Just up here, we need 2n equations for each of the W, the index W. Okay, so that is Q dot I comma W equals epsilon I W. So that's our band specific emissivity now, epsilon I W. Still AI EB I W minus J I W over 1 minus epsilon I W. And that's for I equals 1 to n, and for W equals 1 to NB. So you can see you have this whole other dimension, right? We're kind of exponentially increasing the number of equations we have to solve based on the number of bands that we choose, but it's really just bookkeeping, right? You're just solving more equations, just bookkeeping. The other set of equations becomes Q dot I W equals AI summation from J equals 1 to N Fij of J I W minus J J W, again for I equals 1 to N, and for W equals 1 to NB. Okay? So the only thing that changed is I added a W index, and we have to do this with inside 2 duplicate loops, basically. Questions on this before we look at ease? Okay. So let's remind ourselves the problem again. Right, we're doing the same thing, but now let's say that we have our emissivity, but here on surface 4, let's say I'm going to break this surface 4 into 2 bands. So I'm going to say if we're below 8 micron, my emissivity is 0.8. If we're above 8 micron, it is 0.2. Sorry, 0 to 8. What is this? 0 to 8, 8 micron. Oh, lambda is greater than 8 micron. It's 0.2. So okay, that's the separation there. And then surface 1, we're going to do something similar, but we're going to make the cutoff 22 micron. So we have a 2-band surface, and we have a 2-band surface. Yeah?
Does this mean that there could be like different number of bands per surface?
Yes. Sort of. And the sort of is what I was going to say next, which is how does this change how we approach this, right? The fact that you have a cutoff that's different for each surface. So we'll say it this way. If you went in and made a 2-band model and said, I have W equals 1, W equals 2. And W equals 1, you threw in the first value here in both cases, and W2, the second value in both cases. That's wrong, right? Because you have this middle bit where they overlap that one of the two is incorrect, depending on how you choose it. So this is not a 2-band model, right? This has to be a 3-band model. You have where both are at their low value, where one is high, the other is low, and then where both are at their high value. So you have to look at how the problem is specified and then decide whether you need 2 bands, 3 bands, whatever it might be. If it so happens that you have like 10 bands, but the bands aren't lined up with your other 10 bands, well, that means you got 20 bands, right? So I think it's a good idea as you're discretizing this, if you can, get the data to line up with the bands that you want to put in your model. Sometimes it's just not possible, but this situation warrants 3 bands, okay? So that would be, I guess, 0 to 8, 8 to 22, and then above 22. So we're going to implement that in ease. Let's look at how that is done. So we'll flip over to this example. So these are both in the folder, by the way, gray, and then this is semi-gray. So here we have our semi-gray problem. You'll note I added a bunch of crap here with emissivity as a function of now surface number, so 1, 2, 3, 4, and then band, W, 1, 2, 3. So in surface 1, I have band 0.9. This is going to be from 0 to 22, I think that's what it was. And then band 3, it's 0.5. This is 0.5 everywhere. Here we have 0.7 everywhere. And then this is the other where it's 0 to 8 micron. Then above 8 micron, it's this one. So just you're keeping track of how that works. I've also got a specification of the band width. So 0 to 8, 8 to 22, 22 to some big number, right? This is effectively infinity. You just want to make this number big enough that the answer stops changing, but you can't put in infinity into the blackbody function, unfortunately. So these are the bands. View factors stay the same. This is, again, from surface I to surface J. And then down here we have, instead of our duplicate I equals 1 to 4 black stuff, we have now we have to look at the external fractional function. So it's in ease, that is black body. So black body at the temperature over the wavelength band times sigma t to the fourth. That gives us EB for that band W. Okay, once we have that, then we can go in, do the equations for surface balance and then radiosity balance. And we have, again, we're doing this for each I and each W. And then the last thing, and the thing that's new, I guess, is we have to sum everything up. So this now is summing up for each surface, 1 to 4. We're summing up the heat transfer in band W, right, for our W equals 1 to 3. So this is new. I guess in this problem we are saying, well, before we head it this way, let's just keep it the same way. Probably won't solve now, but we'll see if this works. Okay, so we should be able to solve this. And now we'll see what's coming out of this in the arrays tables a bit more complex. But we have EB in each surface and then in the different bands. So we have the 3 bands. Before there's just 1 column. J is similar, we have 3 columns. Q is Q dot similar, and then here's the total, right? So that's, I guess, how that works. Questions on that? Okay. We could, just for fun, because we have a couple more minutes, make this 0. So let's say we wanted to make one of the surfaces adiabatic. That happened to be, I guess, solving for this value to make the surface adiabatic. So we could do that. And how does that change anything? OK, so it's adiabatic, and my temperature was a little bit wrong. But you can do that, right? Again, in Python, you'd probably want to just set it up as like a matrix and then do a matrix inversion or something like that. OK, let's see what else we have here. Nothing. So that means, I guess, thank you for being part of the class. I've really enjoyed having you. You guys have been a great class, a lot of fun. So thanks again, and best of luck.